In this session, I will share the knowledge I learned in the chip making process. And before I start, I'll introduce you certain terminologies. One is application specific IC, ASIC. So, I mean, many people may not be familiar with this term, but if you become a chip maker or chip designer, you will keep hearing this term ASIC, which is application specific IC. So I'll elaborate a little bit on that. ASIC is a chip which is specifically designed for an application. For example, a memory chip is not an ASIC. Memory chip is a general purpose IC. It is an IC, but it is not an application specific IC. And ASIC is nowadays used as a common terminology for microchip in general. So today we will be going through the basic concepts of ASIC development. I will start from the types of ASICs, types of ICs, and I'll all the way go up to I'll show to you how a chip can be designed in, say, 30 minutes. These are the topics I covered today. I will give you an introduction to microchips, different types of ICs, and a concept called a system on chip. So this is a special kind of chip which makes the electronic design extremely low cost. I mean, you can integrate a lot of components or a system into a small chip using the concept called the system on chip. I will give you a brief introduction about that. And I'll also go through certain concepts of ASIC design flow. I mean, what are the steps involved in a ASIC? ASIC means microchip. ASIC design flow, what are the important steps in that? And I'll give you a small exposure to RTL design. RTL design is the way of designing a chip, or defining or specifying a design in a high-level language. That is RTL design. And also, I'll give you a glimpse of verification technology and the basic implementation flows in a microchip design. And the 30 minutes concept I mentioned, how to design in a 30 minutes, how to design a microchip in 30 minutes, that comes from the field programmable gate array. So I will give a brief introduction about that. When you hear about microchip, you think that, oh, it's only one type of, these are all chips, right? So, but there are different types of chips there. One is, if you take the case of, this is a LM317 chip, which is actually an IC. So this comes in the category of analog IC. If you look at the analog IC, the core will be analog. There will be IOs. These are small strips are called input outputs, the IO pads and IO logic, and that will be analog too. Anyway, IO logics are always analog. So the core is analog here. That's why it is called analog IC. The digital components are not there in this kind of designs. And there are certain types of ICs called digital ICs. Okay, even though they are called digital ICs, they are not completely digital. So if you look at the periphery of the chip, they are all analog IOs, and then you have a core called digital core. So I mean, when you say core, means that is the functionality of the chip is actually happening in the digital, the core. And the IO helps you to communicate with the external world, like how to talk to another chip in the board. So that is what is meant by these IOs. So the core takes care of the functionality of the chip, and then the IOs helps you to communicate with the external world. For example, Intel Celeron processor, Intel Atom processor, or for example, a Qualcomm Snapdragon processor. These processors have lot of digital cores and analog cores. For example, they might have a USB transceiver inside the chip, which is a fully analog circuit, and it will have the silicon CPU cores, which are completely digital. So nowadays, most of the advanced chips are mixed signal chips. So they have both analog core as well as digital core. Let me explain that. Digital means you are always dealing with the two voltage levels, 0 and 1, and 0 will be represented by certain voltage level and 1 will be represented by another voltage level. So you are talking about Boolean states. And when it comes to the analog IC means it is a linear change of data, linear and non-linear. I mean, basically, it is not restricted to 1 or zeros. It is restricted to all the voltage levels within the range. So, so that makes the chip design methodology for analog core and digital core different. So now let's come to a different concept. This is a typical motherboard. If you look at here, you see a motherboard. There are multiple chips in a motherboard. So, for example, if it is a old say Intel motherboard, you will see a like a north bridge, south bridge chip. You will be seeing a lot of Ethernet chips. You will be seeing external graphics controller chip. So, in traditional motherboards, you will see all different kind of chips communicating each other, doing the function of the motherboard. But there is a new trend. When you keep designing these multiple chips, they increase the motherboard cost, because you need to have too many components in the motherboard, and motherboard become extremely expensive. And also the chips need to communicate in a very high speed. So since IOs cannot toggle as much speed as the core, you cannot run the chips at a very high speed. So the new trend is to integrate them all into a single chip. So bring the entire system into a chip. So that is called the system on chip. So instead of all these chips separately sitting on the motherboard, all of them are integrated into the single die or single chip, and it will the chip will function like a system. It is no more it's no more a chip. It is an entire system by itself. So what is the advantage of that? The advantage of that is you can bring the entire system into a small motherboard. For example, if you take a look at the Raspberry Pi, you see that it's a very small motherboard. How many of, a lot of you might have got exposure to Raspberry Pis and the new generation motherboards and system on modules. So all of there you can see that, oh yeah, there is a very small chip, a very small motherboard, but it is doing like Linux booting, and it is able to do artificial intelligence. It's doing a lot of functions which people could not imagine a few decades or a few years back. But nowadays it's possible because the concept of a system on a chip, where you do a very high degree of integration to a small chip, and that reduces the board cost, that increases the speed of the system, the way the different kind of systems communicate each other, and finally you can put a very small embedded chip in a camera, and you can even do artificial intelligence of video analytics on a small board. When the board becomes smaller, the cost of the system becomes smaller, and the speed at which you can run increases. So a lot of advantages to that. So here you can see that in here all these GPUs, DSPs, Ethernet, DDR memory, SRAM, CPUs, analog devices, and connectors, all of them were there in the motherboard. Suddenly, when you have a system on chip, SoC module, then your external components become extremely less. How many components are here? 1, 2, and the connectors. Whereas here you have all different kind of components on the motherboard. So that is the level of integration the system on chip brings to the electronics devices. So this is just to give you an understanding of what is happening in the system, in the IC world. So now let us take a look into what is there inside a microchip. Okay, so I am taking the example of a system on chip, an SoC. So in a chip you have, so this is a chip, this is the plastic, and there are leads which are used to solder the chip into a motherboard. And inside the chip, there are CPUs, there are digital IP cores, there are SRAM modules. SRAMs, as in, for example, a cache is an SRAM. And there are different kind of analog IPs. For example, analog IP example is a PLL or a DDR driver. So these kind of things are there inside the analog IP. So these are the designs inside a typical system on chip. Now, so how this system on chip will look in a layout. So this is another view of this chip. This is a logical view or a system view of the chip, but this is the physical view of the chip. Okay, this is what a chip is. I mean, this is this is a software. This is a software data or a like electronic data. But even if you open up the plastic of the chip and use a microprocessor, like a small a microscope, you will see something similar to this. Okay, so this is a layout. This is actually the layout of a processor or an SoC, and I am saying that even if you open up this case, this particular plastic, if you remove the plastic and look into the chip, you will see something similar to this. So this is how a chip finally goes to the foundry for fabrication. Okay, I know I will be keep on introducing some new terms called the fabrication, things like that. This is just to give you up to speed with what are the terminologies in a chip design field. Don't get like too much scared with these terms, but just for you to understand what are the things. So this is the final chip layout after designers complete their design, verification engineers complete their verification process, the place and route guys complete their place and route. After all the flows required to execute a chip making process, finally you get this chip layout diagram, and this is what finally mostly you will send to the foundry for manufacturing the chip. So now I think we are coming very close to the real things about chip making. Okay, so far I just talked to you about what is a chip, just to keep you up to date with that. So now we are coming to the actual data. So you are most of you are familiar with this kind of diagrams. What is this? This is a D flip-flop. What is this? This is a NAND gate. So I mean, most of you are familiar with this. So in a chip, in a digital design, these are the primary building blocks.